Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Today's session, we're going to continue with our EMT lecture. So the issue that, inshallah, that I'm going to discuss relate to week number 4 based on our weekly schedule, which talk about potential difference and energy density. Okay, that's going to be our topics that we're going to talk about in this particular session. Okay, so the first question that maybe some of you would like to ask, how does the current topic relate to the issue that we discussed before? Okay, so therefore I'm going to answer that question by giving you the overview of what we have learned and how those issues that we have learned is related to current topics, which is regarding potential difference and energy. Okay, so let's recall what are the current field that we are currently in, and most of you will answer we are talking about electrostatic field. Okay, from electrostatic field, we know the source are stationary charges, and one of the source we're going to use to represent all the other sources is the volume charge. So therefore, we're going to start with the source. So volume charge density. Okay, that should be our current source or common source for electrostatic field. Then from the source, we know it's going to emit two major types of field, which are electric field intensity and electric field density. So that should be what we have learned. So now we're going to talk about something common to us, mostly for electrical engineers, which are potentials, V, okay, and then energy, WE. So therefore, this should be the next step that we're going to discuss. So we're going to link between the current issue that we have learned before with regards to all the parameters that we have discussed before. So in this sense, what we can conclude in EMT, whatever we learn now is depend on the issue that we mentioned before. This is why EMT is one of the toughest subjects in electrical engineering because of that reason. They are interrelated. So in order for us to understand about potential, we must understand about electric field because they are interrelated. So that's why it's no sense learning EMT just to keep it at the end of the semester, because we need to follow the flow systematically because they are dependable. So as you can see before, the E depend on the charge, the D depend on the charge. Now the V will be depending on the E, and the energy we're going to prove later on will be depending on the E as well as the D. So if we don't understand about the D, we can't talk about the energy. Similarly, when we don't understand about the E, we can't discuss about the potential. So that's why make electromagnetic subject is a tough subject to learn because they are dependable between each other. The thing that we learn in week number 1 still applicable in week number 4. Okay, so we're going to talk about what is the issue now, the potential. With that, I'm going to give the title of our discussion as something quite different than what we intended, even though we are saying we want to learn about potential. But the best way to talk about the potential, we talk about something else, which is energy exchange. That's what we're going to discuss, energy exchange. And you will see later on how this will relate to the issue of potential. So energy exchange in a system of charge. Okay, that's going to be our starting point when we talk about potential. Energy exchange in a system of charge. Okay, let's say you have a system containing electric field. Okay, so let's say you have a system contain electric field as shown here. So the red line is our electric field. So the direction of our electric field is from left to right. Because we know electric field is a vector entity, so it has magnitude as well as the direction. So the issue now, if I throw into the system or the space here a charge, and we want to make it specific, we call it a point charge. So let's say we throw a point charge Q into this space. Okay, so we throw a point charge into the space. So what will happen to this point charge? So what will happen to this point charge when we throw into this region containing electric field? And we have learned before, when we have a charge and electric field, we're going to introduce what is known as force. And the force will be in the same direction as the E. So in other words, the charge will move in the direction of the electric field. So mathematically, when we have force and distance, okay, let's say the distance we denote here as small movement dl, we're going to introduce as the term known as work done. Okay, so we call work done, but this work done is done by the system. We just observe. Okay, we can see the point charge moving by itself. We don't have any say. So therefore, we just observe. So we can conclude that as work done by the system. So we're going to say there, work done by the system. So mathematically, it should be dWe. Okay, and then we're going to say is equal to, what is it? Force F dot dl. That's how we define work done. Force multiplied with length. And we know force is a vector, length is a vector, so energy is a scalar. Therefore, we must utilize dot product in this particular calculation, where we are saying that F here, based on our previous discussion, should be equal to Q multiplied with E. Okay, so therefore that's what should be the equation regarding work done by the system. So in other words, let's say I want to calculate the total work done. For what is mean that I want to determine what is the total work done for this point charge to move from a point A, let's say, to a point B. Okay, so the total work done going to be what then? So therefore I'm going to rewrite now total work done but still remember this total work done is done by what? By the system. So I'm going to call it to be WE. Okay, so I'm going to integrate because we know that is the case. It should be F dot dl. From which point to which point is our limit of integration? Yes, from point A to point B. So let's say this is our equation number 1. Okay, so equation number 1 is the total work done by the system when the point charge is moving from A to B. Okay, but human being character always want to control things. Okay, we usually don't allow something happen automatically. We want to be dominant. Okay, let's talk about that view now. So let's say we have the same system. So the system contains of electric field as before, shown here. But the only difference now, we want to control whatever happen now. We don't want to allow the charge to move by itself. So let's say we want to control it. So what's going to be the worst case when we throw a point charge into this region? So you want to control it. So now, if we allow the system to do it, we know that this point charge to move according to the electric field, which is to the right. But as a nature of human being, we want to control whatever happened in that particular region. So the worst case situation is that we purposely move the point charge directly opposite to the E field. Okay, so that should be the worst case scenario. We call it to be F force applied. Okay, you can see the difference here on the left. The charge moved by itself automatically. On the right, the charge is being moved by us. And then the worst case scenario is that the direction of the movement will be directly opposite the electric field. So that's the most maximum maybe energy that we have to spend in moving the point charge. Okay, and as you can see, when the charge moves, okay, it's going to create change of length. And we know that in physics, when you have force, you have length, we're going to create an entity known as energy. So now what we can define, okay, so work done, still the same thing, work done by, is it the system now? No, by external factor. Okay, you can see by the system, the charge moves by itself. So now we move it directly opposite to electric field. So now we are saying work done by us, by external entity. So mathematically, we can define that to be dW. Then, so the force now we're going to define to be F applied, a vector. We're going to dot with dl. So that's a simple mathematics of work done. Force multiplied with the length. Okay, as shown in the diagram. But the difference now, we produce the force. Okay, so therefore, and then we know that for worst case scenario, the F applied now, we define to be what here? Okay, from a simple diagram, we're going to see charge still there, but now the field going to be opposite. We're going to call it as QE. Okay, so you can see the difference now. Here is Q multiplied with E, but in the second diagram, we call it to be minus QE. Okay, so let's say this, we want to calculate the total. Okay, so let's say I want to calculate the total work done now. Same position A and then position B. Okay, let's say now we're going to define now total work done. But now the difference here, this total work done by external. Okay, so what should be mathematically? So should be WE, still the energy, electric energy that we want to calculate. But now, as you can see, it's moving from where to where here? It's moving from B to A, agreed? That's what we observe from the mathematics, B to A. And then it's going to be F applied dot with dl. Okay, so this is going to be equation number 2. So we have two set of equations. Equation number 1 is the total work done by the system. And for equation number 2 is the total work done by external. So let's compare these two equations. If you compare mathematically, I think you will agree with me that they are actually resulting with the same solution. So let's substitute now. So we know that here, going to end with integration from a to b, and then I'm going to substitute now QE dot dl. So that should be our equation number 1. For the second equation, we're going to see now as integration from where? B to A, and then should be minus QE dot with dl. So what are the difference between these two equations? I think you agree they are exactly the same. Okay? But we can see that not the final result is important here. The process of getting the output is important. As I'm repeating now, for the first case, the equation based on work done by the system. For the second equation, it refers to work done by external, even though the final result giving you the same output. Okay, so for us here, it's not the final result is important. What's important here? The process of getting the final result. So I'm going to explain it further when we talk about potential difference. Okay, so let's recap this equation. So number 1 and number 2. Okay, so now I'm going to go to the next issue now. What is potential difference? So that's what we're going to talk about. What is potential difference? Okay, to talk about potential difference, I'm going to refer to our handout number 6. Okay, so if you open handout number 6, you're going to see this particular page. So this is what we're going to focus on, the wording inside this box. Okay, so let's read together what it says inside this box. Okay, it said here, potential difference, VAB, is work done by an external source. Okay, from this statement, the first part of the sentences, okay, which equation that this is more relevant? Equation number 1 or number 2? Because it's clearly stated here, work done by an external source. I think most of you do agree with me. This sentence do relate more to equation number 2, because we defined just now equation number 2 is the total work done by external. So now the definition of potential difference is work done by external. So meaning that equation number 2 is the one that we're going to reflect. So this equation number 2 is the foundation of potential difference that we're going to use. Okay, so what important here? He said here, in moving a unit positive charge, when we can see there's a term Q here, that's representing point charge, but the definition of potential difference insists that this point charge is having value equal to 1. Okay, because unit point positive charge meaning that the Q is equal to 1 from point B to point A, from point B to point A. So therefore, what we're going to do now, we're going to define potential difference by equation. Okay, so I'm going to rewrite now what we extract from the information of potential difference. So potential difference okay, VAB, okay, we're going to use VAB is equal to minus B to A E dot DL. So this is the equation of potential difference. It comes from equation number 2. Okay, the total work done by external source, but we need to alter a bit of equation number 2 where the point charge is having the value equal to 1 coulomb. So this is going to be the equation to determine potential difference. And you can see potential difference do depend on the information of the E. And how we know, how we obtain the E is important here. Unable to determine the E field, we cannot proceed to determine potential difference. So that's what knowing Coulomb's law, knowing Gauss' law is important. Because from the E that we extract from those two laws, then only we be able to determine the potential difference. And then we know the unit for potential difference is volt, the one that we always use when we talk about potential in circuit theory or in other electrical subjects. So this is a fundamental definition of potential difference with regards to electrostatic field. Okay, let's do one example now. So very simple example. Oh, by the way, for those who want to know how the issue that we're discussing relate to our textbook, so you can refer to page 144. For those who want to refer to the textbook, potential difference discussed in quite detail by Sadeku, page 144, and then the section is given by section 4.8. Okay, for those who have the books already, you can go to this particular page and section, then you can read yourself what is potential difference. But I'm just discussing in terms of summary, because I'm just going to extract what's important that need to be known, and I'll explain you based on what is related to just now, energy exchange. Okay, so what I'm going to do next, I'm going to do example. So let's do example. So example, okay, let's say you have a point charge. You have a point charge. My point charge value is Q coulombs. Okay, so we have a point charge. So in order to make the mathematics easy, we're going to assume the point charge is located at the origin. So I'm going to draw my axis now. So this is my x-axis, this is my y-axis, and then this should be my z-axis. Okay, so now let's say I have 2 points in space. Okay, one point I'm going to denote as point A. Okay, so this is my point A. Another point I'm going to give it as point B. So since the field generated by this point charge do obey spherical coordinates, so I'm going to use spherical coordinate parameter to define point A and point B. How I do it, I'm going to define the radius of point A, okay, is given as RA based on spherical coordinate, and the radius of point B I'm going to define as RB. So what should be the question? So the question said, determine VAB. So meaning that the question wants us to calculate what should be the potential difference between point A and point B. Okay, so that should be the thing that we want to do here, to find the potential difference between point A and point B. And we know that the way to find potential difference now is based on the equation that we just defined just now. Okay, so we know that VAB can be calculated by using the above equation. In order for us to use this equation, we must be able to define what is the E, and then the E is electric field intensity. And from this diagram, we know that the E actually the field emitted by the point charge. Okay, so therefore we know that the E actually the field emitted by the point charge. So what should be the E due to the point charge? So there are two methods that we can use to find the E, either by using Coulomb's law or Gauss law. Okay, so therefore electric field, so now I'm going to use this equation. I'm going to define now from Coulomb's law, or you can also use Gauss law. The E emitted by our point charge going to be equal to Q divided with 4 pi epsilon naught R in R direction. Should be R square here. Yeah? Okay, so therefore that should be the equation of the E. So this equation based on spherical coordinate. So therefore what we can do, we can substitute the E to this equation. So we're going to end with negative, should be Q over 4 pi epsilon naught R square in R direction dot with dl. Okay. Now, what should about the dl here? So for us to substitute dl, we must refer back to our handout of handout number 2. We have table, and then from our table we know that the dl based on spherical coordinate should be what then? Should be dr in R direction plus R d theta in theta direction plus R sine theta d phi in phi direction. That should be our dl based on spherical coordinate. Okay, so what we're going to do now, we're going to solve the mathematics by utilizing dot product, the dot product. So therefore R dot R will give us 1. R dot theta direction will give us 0. Similarly, the direction of R dot product with the direction of phi also end with 0. So the final solution will only based on dr component. So for us, dr is the important variable need to consider. So the limit that we're going to choose must based on the R factor, the radius. And then we know that for point B, the limit should be RB. For point A, the limit should be R. So let's substitute now. So here should be RB, radius of B. Here should be RA. So when we do that, so the final solution that we're going to determine now, VAB, okay, is equal to Q divided with 4 pi epsilon naught. Okay, and then it's going to be 1 over RA minus 1 over RB. So that should be the solution of potential difference between these 2 points when you have a source of point charge in that system. Okay, so therefore that should be our solutions. Okay, so I'm sure it's not that difficult. So that should be the way we determine potential difference. Again, in this particular example, it's important for us to know about the E. So let's talk about the solution that we are getting here. Anything special that you can see from these solutions? Okay, so you can see Q is the charge. Everything here is constant. 1 over RA is depending on the position here. 1 over RB is depending on position here. So let's talk about the definition of potential difference. Remember, potential difference is work done in moving a point charge 1 coulomb from point B to point A. So you can see now, you are moving the point charge from B to A. So you creating a path, or in bahasa Melayu, laluan. And you can see from the solution here, there's no consideration, no relationship with regard to the path. Okay, you just mention here a point, and everything constant. So there's no sense of path. So if I'm taking my my point charge from B to A using this path, is going to be the same when I'm taking my point charge from B to A using this path. So in other words, our solution here is independent of path. That's what we can conclude here, independent of path. Yeah, laluan. Because you have to remember, potential difference adalah kerja yang dilakukan, membawa charge titik bernilai 1 coulomb, membawa charge titik daripada titik B ke titik A. So you are moving a point charge from B to A. So you need a path. So therefore, we can see the result is nothing to do with the path that you are taking. So whatever path you are taking to move your point charge, the final solution still remain the same. Therefore, what we are saying now, the result of AAB is independent of path. So let's discuss that further. So what I'm going to do now, I'm going to assume, okay, we have different scenario now, 2 points. Okay. So let's say we have point, okay, here. I'm going to call it point B, and then this is point A. Okay, so when I move a point charge from B to A via this path, I'm going to create potential difference. So let's say we call this path number 1. So therefore, I'm going to say VAB1, because I'm depending on path number 1, is equal to negative B to A E dot dl. Okay, so that should be the first potential difference that we are calculating based on the equation, and we can see the path taken to move the point charge as shown in blue color. Okay, now let's do the same thing now, but different path now. So I'm going to say to myself, okay, I'm going to move the point charge from B to A, but via another path. I'm going to define that to be path number 2. So then also going to create another potential difference. I'm going to call it VAB number 2. And then mathematics should be equal to negative B to A E dot dl number 2. Come take a path number 2. This one we call it dl number 1. Okay, so then can I say to myself, just to make it mathematical argument, can I say now that VAB1 is equal to VAB2? Can I do that? Can I say that VAB1 equal to VAB2? Yes, we can do that. Okay, so let's make it more detailed now. What is VAB1 equal to? A negative from B to A E dot dl number 1 is equal to negative from B to A E dot dl number 2. Okay, so if I move the second term to the left, what I'm going to have then? I'm going to have now negative from B to A E dot dl number 1, and then should be plus, okay, and then should be what now? Integration of B to A E dot dl number 2, and this will give equal to 0. Okay, so just to make the mathematics slightly revert back to the definition of potential difference, I'm going to make it equal to now negative here, but I'm going to change now this term A and this term becoming B. Okay, so it's still valid. Okay, so I'm going to explain why later on. So let's go through this mathematics now. So let's talk about the blue equation. What I said. So this equation state that I'm taking a point charge from where to where? From B to A via which path? Path number 1. So what we are doing now, we are moving our point charge, okay, from B to A. So I'm going to take this path now, B to A. This is what we are doing now. Okay, based on what? Based on this equation. So I'm taking my point charge from B to A via path number 1. So this is what we're doing, B to A. So then I'm going to continue with the second term of the equation. So negative meaning that work done by us, by external. Now I'm moving from where to where? A to B. So I'm going now moving from A, I'm moved to B. Okay, initially B to A, now A to B. But now with the second path, path number 2. So I'm starting from B, I'm ending at B. So in other words, what we are saying now, if I'm doing completely closed integration of the E dot dl, the solution to it is equal to 0. Okay, that's what we are saying now. Because you can see from the mathematics, it's starting from B, is ending at B. So if I'm starting from B, I'm moving all over the places but ending again at the same point B, the total work done by me, which is external source, is equal to 0. Okay, so this equation is important. It's only true for the case of electrostatic. And this relates to Kirchhoff's law in circuit theory. Okay, so again I'm repeating, this equation is only true for the case of electrostatic, and we call this equation as Maxwell equation number what now, you think? Yes, number 2. So we have seen Maxwell equation number 1 before. So now we are defining Maxwell equation number 2. But I'm going to say this equation only valid for electrostatic field. When we talk about electromagnetic field, this equation need to be adjusted according to different type of field that we're going to encounter later on. Okay, so that should be the first observation we conclude from our result. So we are saying for electrostatic field, because the source is stationary, it's producing electrostatic field, the work done in moving a point charge from one location, and then we carry the point charge all over the places, and then we carry it back to the same initial location, the total work done in moving that point charge is equal to 0. Okay, so that should be the first observation that we are seeing from the results of this example. Okay, for the second observation that we're going to ask now is about reference. Okay, reference point. So meaning that we have VAB now as a, so let's rewrite it in new page now. Yeah, so I'm just not going to make it overcrowded. So let's recall again our solution saying that VAB, okay, potential difference between A and B is equal to Q divided with 4 pi epsilon naught 1 over radius RA 1 minus radius RB. So that should be the solution that we have. So now I'm going to ask you, because when we have potential difference, we always deal with what we call it reference point. Okay? So that should be the situation, reference point. So I'm asking you now, between point A and point B, which one is our reference point in this equation? Is it point A or point B? Okay, so for me, I'm going to define point B is our reference point. Okay, so we are saying now point B is our reference point. So what happened is, if you're given this scenario, okay, if, okay, RB is assumed to be located at infinity. So what happened to the mathematics of the above equation? So we're going to say now, VA infinity is equal to Q divided with 4 pi epsilon naught RA. Okay, so therefore we're going to see 1 over infinity is becoming 0. So in other words, we can rewrite this equation to be VA. What's special about it? You can see now we are defining a point. When we talk about potential difference, you need to have 2 points at least, okay, A and B. So therefore, we're going to call that as a potential difference. But now what we are saying now is only 1 point referred to this particular equation, where we assume the reference is located at infinity. So when you have this particular term being asked, this potential, we define it to be called as absolute potentials. Okay? So what is absolute potential? When you've been asked to find a potential based on 1 point in your problem. If you've been asked to determine a potential between 2 points, that is known as potential difference. But when we've been asked to find only a 1 point potential, so that is defined as absolute potential. In other words, we are assuming the reference point is located at infinity. Okay, so maybe you bit wonder what is happening now. So let's recall, let's say you are being asked to work in this particular situation. Let's say you have a circuit now. So let's say a circuit contained by this red box. So when you want to find the potential, 2 point in this particular circuit, so we can define that to be known as potential difference. Somehow, let's say you want to analyze this part only. Okay, you don't want to bother about this particular part because maybe you are zoomed into that particular part of the circuit. Now we can see in this working region, there's only one point. So when you're dealing one point situation of potential, that is defined as absolute potential. Okay, so that's usually the case because when you work in designing a circuit, maybe integrated chips, you have to zoom into certain part of that particular circuit. So zoom in, so therefore you only have one point to determine the potential. So therefore that is known as absolute potential. Okay, so what we are saying now, so using this equation, we can conclude now potential due to a point charge okay, so you're going to call it as V now, should be equal to Q divided with 4 pi epsilon naught R. Okay, let's draw it now. Yeah? So just make it easier for us to observe. So let's say this is our point charge. I'm going to call it Q. So I want to find what is the potential here, and we can see only one point. So we call it absolute potential because we are assuming the reference for this potential is located not inside this paper, is outside, so it's infinite. So we can find the V here as Q, okay, and then the distance here, this distance we call it to be equal to R. Okay, so that's what we can determine the potential from the charge. Okay, so remember the first way we determine the potential from what? From the field. Now, we also can determine the potential from the information of the charge without finding field. We are jumping, meaning that we ignoring the field. We just refer to the charge. From there, we can determine the potential. So let's say you have more than one point charge. Let's say I have another charge here. Okay, so I'm going to make it to be Q number 2. Okay, so now since we have more than point charge, I'm going to denote this to be Q number 1. Okay. So let's say we have another point charge. Let's say make it to be here. So I'm going to call this to be Q number 3. Okay. So what we can conclude now, the potential due to 3 different charge, V is equal to V1. The potential due to Q number 1, where the R here is R1, plus V2 due to the point charge number 2. And remember the distance now, we define it to be R2 plus V number 3. And the distance here we denote to be R3. So in general, we can say summation of Q I over 4 pi epsilon naught R I from 1 to 3. So that's what we can conclude when you have more than one point charges. Okay, so therefore we expand the idea of one point charge into multiple point charges, but yet the foundation, the equation remain the same. Okay, so now, so let's because we know that our source not only consists of point charge, So there are second type of source that we learned before known as continuous charge. Okay, so now I'm going to extract the information but relate more to our continuous charge. And the most basic continuous charge is known as line charge. So let's say we have a line charge now. Okay, so we know that the line charge is known given as total charge Q okay, and then we know the total length is L. So what I want to determine now, what should be the potential here? What should be V here? The potential due to our line charge. And we know that when there's only one point of potential, we are saying it to be known as absolute potential. So we're going to use the idea that we developed from the system of the point charges, where we're going to take sample. Okay, I'm going to take sample now. First sample is here. Okay, this sample is dq. Okay, then the second sample is going to be blue color. Let's say make it here. So dq. And the third sample, let's say down here, red color, also dq. Okay, I think you can see what we have defined before can be used. Okay, remember just now, when we have a point charge, Q, we're going to produce V. So our sample now is acting as what now? As a point charge. But the magnitude of this point charge is what? dq. Okay, so we have a point charge Q is going to produce the potential V. Logically, if we have a point charge dq, it's going to produce potential value equal to dV. Okay, so now this dq we're going to produce dV here, black in color. This dq, which is blue in color, going to produce another potential dV, blue in color. And the red sample here also going to produce dV, red in color. So if I want to calculate the V, I have to sum all the dV that been produced by all the sample. Since the source is continuous, I'm going to change the sigma to become integration, and it's going to be dq over 4 pi epsilon naught r. Okay, and then this dq we have to substitute according to what type of source we are dealing here. For this particular situation, it's going to be rho L d L. Okay, so if we expand this equation for other source, let's say what happened to the surface charge. So this dq going to be substituted with rho s d s, and finally we are dealing with volume charge. We just need to change the dq here with rho v dv. Apart from that, all remain the same. Yeah, the 4 pi epsilon r remain the same. The only thing need to be changed according to which type of source is the dq. So let's summarize now what we have learned here. Yeah, so I'm just going to recall back what we need to know. So we said now in electrostatic, the source, I'm summarized now. Yeah, the source is rho v. It's going to emit electric field. It's going to emit electric field density, intensity, density. Now we have learned there's V, okay, potentials. And the V can be calculated based on the first approach example we did from the E. Okay, so this we are using minus E dot dl. That's one approach that we can use to find the V. And the second approach to find the V is from the rho V. Okay, so we are saying now this should be the integration of rho V dV over 4 pi epsilon naught r. So in other words, there are two methods that we can find the V, either from the information of electric field or information of charge. Depend on you, which method do you want to use to determine the V. Yeah? It's up to you. Sometimes a student will feel the first method is easier because the mathematics is less complicated compared to the second method, but depend on the student. So it's up to you which method that you want to adopt. But whatever you're going to do, you must always remember the V can be defined in two ways, either potential difference or absolute potentials. Okay, so that should be our conclusion based on the discussion until now. I'm going to talk about energy later on. So I'm going to end my discussion here by doing examples. Shall we do example now together? Yeah. Okay. Examples. I'm going to use a problem from handout number 4, question number 2 under the Gauss law topic. Yeah. Okay, so refer back to handout number 4. Okay, question number 2 under the segment of Gauss law. Anyone recall the question? Still remember? Yes, I'm sure some of you do remember. We just solved it recently. It's been discussed in my video titled, if not mistaken, tutorial number 5. Yeah? So what is given in that particular problem? You are given a sphere. Okay, a sphere with radius which is A. Okay, and then we have a charge given by that problem consists of surface charge rho s. Okay, so let's say we start with that particular structure, the structure that's quite familiar to us. But the only difference in this example, we want to determine the potential. So the question said, find V in all regions. Okay, that should be our question now. Find V in all regions. Okay, so how we start solving this problem? Let's recall our last diagram that we developed together. So this is the diagram that we are referring now to plan our approach. Okay, meaning that usually when I want to solve ENT problem, I need to prepare my method because there's so many ways that we can use to solve the same problem. So I'm going to ask myself, am I going to use method number 1 or method number 2? That should be the first thing I'm going to ask myself. Method number 1 or method number 2? Okay, then the second issue that I'm going to ask myself, this V, is it potential difference or absolute potential? That's going to be the issue I'm going to ask myself when I want to solve this problem. Okay? The V asked here is it potential difference or absolute potential? Then once I decide the V, I'm going to use either method 1 or method number 2. Okay, so that's going to be the thing you will ask yourself when you want to solve maybe other problem regarding this type of issue later on. Okay, from my experience here, okay, I'm saying word experience now, I can say that the V, okay, is absolute potential. Okay, let's say I want to define a point here. Okay, so that should be the V. So therefore 1 point. Okay, so I do not know the reference, so I just said V here. By assuming 1 point, I'm assuming the reference is located at infinity. So it's easier for me to define the V in this problem as absolute potential. If I'm defining as potential different, where is my reference? Maybe my reference is different than other student reference. So therefore, we're going to have different solution every time. So by assuming now the reference is located at infinity, and we want to determine the potential due to 1 point in this particular position, inshallah we're going to have same solution. So therefore, that's going to be my choice, absolute potential. Okay, the second thing that I'm going to decide which method. Method number 1 or method number 2. Okay, so I'm going to use method number 1. Why? You're going to see later on how easy it is to use method number 1 compared to method number 2. Okay, I'm going to use easier method. So what you can see, the more example you do in this particular subject, the more reliable your decision, because you know from your experience which method is easier and which method is difficult. So the reason why I decide method number 1, due to my experience. Okay, I can use method number 2, but from my experience, method number 2 is much tougher compared to method number 1. So logically here, you have to do a lot of examples in order to make yourself become a wise person, to choose easier method every time you are dealing with electromagnetic problem. Okay. So let's say, so I'm going to use method number 1. Okay, method number 1. So method number 1 meaning that I'm going to use the field. Okay, so what we have now, we have the source. I need to use the field. Okay, I just want to write this so that it's clearer for you all guys to see. So we have the source. You want to find the field. Why we need to find the field? Because we want to use method number 1. So for me to use the field, we also been taught there are 2 methods. Okay, so one method is finding the E straight away using Coulomb's law. The second method that we did using Gauss' law. So I'm sure most of you do agree the second method, Gauss' law, is much more appropriate. So therefore, from Gauss' law, the D I'm going to convert to the E, and then from the E I'm going to find my V. So that should be my plan to solve this problem. Okay, in order for me to use Gauss' law, most of you still recall there are 2 regions, region number 1, region number 2. Therefore, my solution of V also were based on region. Region number 1, okay, I'm going to denote as V1. Region number 2, I'm going to denote as V2. Where V1 and V2, they are not the same. V1 only true for region R less than A. V2 is going to be true for region R greater than A. Okay, so let's recap from Gauss' law. So this method I'm going to, okay, from Gauss' law, so we already done this part already. There are 2 regions, region 1 So we say region 1 R smaller than A. And then from our experience, from our problem solving that we did together, we say that D1 is equal to what? Anyone remember the solution to this approach? Yes, it's equal to 0. Okay, and then we say that E1 also will be equal to 0, because we know that D is equal to epsilon naught E. So if D is equal to 0, E also will be equal to 0. That's for region number 1. And for region number 2, which is for the range of R greater than A, we found that D2 is equal to what? Anyone remember D2? Equal to rho S, okay, A squared over R squared in R direction. Is it correct? Okay. So, and E2 going to be equal to what? Rho S A squared over epsilon naught R squared in R direction. That's going to be the solution of the D and E. So how we get this solution? From our previous example under the topic of Gauss law. Okay, that is the starting point that we're going to do now. So we are here now. We already determined the E in 2 different regions. So now I'm going to go to finding the V. So I'm going to say to myself, okay, I'm going to find here what should be my V2. Okay, I'm going to do for region number 2 first. So what should be my V2? So my V2 should be equal to negative E dot dl. And remember, this known as absolute potentials. So what should be the reference when we talk about absolute potential? Yes, it should be located at infinity. So meaning that I'm saying to myself, it should be from infinity, and then it must go to what here? It must go to our R. What is R? R is greater than A. Okay, so this point is defined by R. This point is not fixed, it's variable, it can move in any position in region number 2. That's why this point do agree with these definitions. Okay, that should be, and then but what we are saying now, to find V2, we must start from the reference located infinity and ending at R. Okay, so that's what I'm doing. So we go back to definition of equation number 1 that we decide to use to find the V. So what I'm saying now, so I'm using this equation, I must move from infinity to R. So what I'm doing now, I'm moving from infinity to this point. So by doing this process of moving the point charge, I'm calculating the potential at this position. Okay, so when I move from infinity to this location in this region, I can see one field exists. Which field is it? E1 or E2? Yes, E2. So therefore, the E I want to substitute here must come from E2. So therefore, mathematically should be equal to negative infinity to R. So E2 should be rho S A squared over epsilon naught R squared in R direction dot with dl. By now we know that dl should only consist of the R direction. I'm ignoring the theta direction as well as the phi, because I know the mathematical dot product R dot theta will end with 0. R dot phi also will end with 0, just to make sure it's not too lengthy here, because I just need to substitute with the term that relevant to the calculation. So when I do that, mathematically it's going to be equal to what now? Rho s A squared over epsilon naught R volt. Is it correct? Yes. So that should be our solution. Okay, so we can see now the potential in this region do depend on the radius. The further away from the center of the sphere, the smaller the value of the absolute potential in that particular region. So let's repeat for region number 1 now. Okay, region number 1. So I'm going to find what should be the V here. Okay, so just change slightly the position so that it's easier for me to explain. So let's say I want to find the V here, V1. Okay, so we know that the distance between the center to this location still remain as R, because it obeys these definitions for region number 1. So therefore R here obey this particular definition, because we are focusing at this region 1 only. Region 2 now is irrelevant, done already. Okay, so now we are focusing in this region. So I'm going to put a dot here. So therefore this dot must be defined by this R, and this R must agree with this statement, R smaller than A. So I'm going to calculate now what should be my V1. So the formula I'm going to use is standard formula, remember, minus E dot dl. Okay, so this V1 is known as absolute. So absolute by default, the reference should be at infinity. Okay, and then the ending point should be where you want to find the V1. Here. Therefore, the limit should be R. So what I'm going to do now, I'm going to assume infinity located here and R is located here. So what we have to do in order to translate this term is moving the point charge from this position to this position. So that's what we are doing. So you can see that movement will create different field definition. What I'm saying here, you can see clearly from the diagram, from this location, infinity, to this position, R equal to A, the E that reside in this region is E, region 2. We call it E2. And then from this position, moving into this ending position R, the E here is defined as E region 1. So in other words, I can expand the equation according to what I observe by saying from infinity to A, E region 2 dot dl. Remember, the destination is not N yet, because our final destination is R. So I can see now I'm here at the moment, so I have to continue my journey from here to here. So I'm going to follow by this second path. From A into R should be E1 dot dl. That's what you're going to expand based on what you observe. Okay, so now I'm going to substitute what is my E1 and what is my E2. And I can see my E1, okay, I put it here. So this term will end with 0. And this term, I have to use my E2. So now what I'm going to have now should be equal to rho s A over epsilon naught volt. Okay. That's going to be my final solution. So meaning that inside the shell, the potential is constant, whereby outside the shell, the potential is decreasing in value as you are moving away from the center of the sphere. Okay, so that's how you tackle problem about potential. You must be aware the potential, is it absolute potential or potential different? Then you must choose correct method in order to make the problem solving as easy as possible. Okay, so let's note this clearly because we're going to use this information in our future discussion. So with that, I would like to thank you and hope you do understand EMT is a very difficult subject. Why? Because they are interrelated. Okay, every time you learn new topic, the new topic actually relate or do have relationship between the previous topic that we discussed before. So in other words, please make sure you always ready, meaning that you always continue doing revision. You cannot learn at the end of the semester. You must learn from now because what you are learning, the understanding you have now will affect what you're going to learn in our next lecture. So with that, thank you very much. Inshallah, we're going to see each other. Assalamu alaikum wa rahmatullahi wa barakatuh.